In this video, we look at the two common types of data structures, namely trees and graphs. We see how they look logically and physically how they are actually stored in the memory. The structure of the various data types in Python are given here. So we have data types. Data types are in turn primitive or non-primitive. We have three types of primitive data types: number, Boolean, string. 4 non-primitive data types: list, tuple, dictionary, and sets. And I can show the entire structure or the hierarchy of the data types using a diagram like this, where I see a parent-child relationship between one level and the other. Look at the figure on the right-hand side, which is a typical representation of the folder structure in any Windows system. Here again, for example, if we have a look at the folder Intel, it is in turn composed of other folders, and that folder is in turn composed of other folders, and so on. At the root, we have the C drive. Inside that, we have multiple folders, and inside each folder, there are other subfolders. This again forms a parent-child relationship. If the elements represent a hierarchical structure, it is called as a tree. Logically, this is how a tree looks like. It has multiple nodes, and the nodes have multiple branches, and we have other nodes in the various sublevels, and there is a perfect parent-child relationship between the nodes in the higher level and the nodes in the lower level. And if you note, there is only one parent, but there can be any number of children for a parent. Even though this is how we logically view it, how do you think it is stored in the memory? Or what is the physical view of the tree? Is it going to be stored in the manner shown in the right-hand side? Do we have a 35 there, and then in the memory, are they going to be stored literally like how we have a look at in the left-hand side? No. But typically, a tree can be either represented in the memory using an array or using the concept of pointers. Let us see how to store a tree which has a maximum of 2 children as an array. When a tree has a maximum of 2 children at any node, that is 35 has 2 children, 23 and 57. 57 has no children. 23 has again 2 children, that is 31 and 34. That is, maximum children a node can have is 2. When the maximum number of children, similarly, if we know the index of the child, we can always find the index at which the parent is found. For example, if the child is at location 5, the parent will be at the location floor of 5 by 2, which is given by floor of 2.5, which is 2. That is, if the child is at I, the parent is found at the location floor of I by 2. Let us take a tree of degree 3. Here the tree is said to be of degree 3 because we have one node 35 with the maximum number of children 3. Even though 23 has 2 children, the maximum number of nodes any node has in this tree is the node number 35, and it has 3 children, and so we say that the degree of the tree is 3. When we use a linked representation, we have a pointer from 23 to its children 31 and 34. That is, 23 stores the address at which 31 is present and the address at which 34 is present. Similarly, 35 stores the address at which 23 is present, the address at which node 57 is present, and the address at which node 90 is present. A node that is used to represent a node in the tree has 4 parts, 1 data part and 3 pointer parts. Here we have 3 pointers because the degree of the tree is 3. You might wonder, it is not so throughout the tree. At one point, a node has to point to 3 children. At another place, a node has to point to only 2 children. If they are leaf nodes or nodes with no children, then they need not point to any node. So, is it possible for us to give different structures for different nodes in the tree? Generally, when we have different elements in a list, we expect all the elements to have the same structure. This will help the algorithm that we write to move through the elements easily. Imagine writing an algorithm in which in one, the structure of the node has only 3 parts, and in another it has 4 parts, and so on. To avoid this, we ensure that all the nodes in the list of elements that we are trying to process will always have the same structure. So here we have 1 to the data part and 3 pointers pointing to the 3 possible children it can have. That is, 35 has a pointer to 23, 57 and 90. 23 has a pointer to 31 and 34. It does not have the third child, so it points to null. Whereas 90 is a leaf node and it does not have any children, so all the pointers have the value null. Consider some of the common social networking sites like LinkedIn and Facebook, and also the most common networking of devices, namely the internet. Whether it is LinkedIn, Facebook or internet, if you have a bird's eye view of all the people who are associated with it or the web pages that are associated in an internet and how they are linked to each other, the diagram on the right hand side is indicative of how it looks. Here we have many elements in the list, but the elements are interlinked in a manner that they are neither linked in a linear fashion nor are they linked in a hierarchical fashion. This type of a data structure is called as a graph. A graph is typically composed of vertices and edges. Vertices are denoted by the circles. They are the meeting point for the edges. Edges can either have a direction or they can be also represented without a direction. When we represent an edge without a direction, it means that the communication flows between both the edges. That is, if I have an undirected edge between 1 and 2, it means 1 is related to 2 and 2 is related to 1. Let us take an application for this graph. There are 6 close friends represented by 1, 2, 3, 4, 5 and 6, and the number of messages that they send to each other in a day are recorded. If 1 communicates to 2, then there is an edge between 1 and 2, and the number of messages that are sent are given in the edge, and it is called as the weight of the edge. These types of graphs are called weighted graphs because they have a weight associated with each edge, and they are called as directed graphs because all the edges have a direction. Even though logically we look at it as a series of interlinked elements, physically they have to be stored either as an array or as a pointer value. So when they are using an array, we make use of a two-dimensional square array or a matrix. The square array is such that the number of rows and the number of columns is equal to the number of vertices in the graph. There are 6 vertices in the graph, and so we have 6 rows and 6 columns. The value that we write in the matrix is the weight between an edge x and an edge y. For example, between 1 and 2, the weight is 2, so we write it as 2. Between 1 and 6, the weight is 9, so we write it as 9. There is no edge between 4 and 2. There is no edge between 4 and 2, and so we write that the weight is 0. This logical view of a graph has now been converted into a two-dimensional representation. A graph can also be represented using linked lists. As many vertices that we have, so many linked lists are formed. That is, here we have 6 vertices, and so 6 linked lists are formed. In a linked list, a node has 3 parts, 2 data parts and 1 pointer part. In the data part, the vertex number and the weight is stored, and in the pointer part, it points to the next vertex in the series. Let us consider the first linked list that is formed. The first linked list that is formed is to represent all the vertices that we can directly go from 1. From 1, I can directly go to 2, 3, 4 and 6. So, there are 4 elements in the linked list, namely the vertices 2, 3, 4 and 6. In the weight data part, I write the weight in between 1 and 2, 1 and 3, 1 and 4 and 1 and 6. Between 1 and 2, the weight is 2. Between 1 and 3, the weight is 6. Between 1 and 4, the weight is 4. And between 1 and 6, the weight is 9. A linked list is formed between these 4 nodes. We have an array of pointers where the size of the array is equal to the number of vertices. And this array of pointers points to the starting address of the linked list corresponding to the vertex number. For example, first element in the array of pointers has the starting address of the linked list formed for vertex number 1. Similarly, the second array value has the starting address of the linked list formed for vertex number 2 and so on.